This is the answer to homework 10, question 1. So the question asks us to go over a bunch of processes and provide the definition as well as some applications and the different statistics such as mean and autocorrelation. So the first process is the Poisson process, and it's denoted as x of t. It's useful for modeling the times of arrivals entering a system, and it's also referred to as the counting process. So the number of time points in an interval of length t2 minus t1 is a Poisson random variable with parameter where the probability of n t1 t2 is equal to k, which equals e to the negative lambda t times lambda t to the power k over k factorial. So the number is a random variable where n is it's n of t1 and t2, and the time points are ti in an interval, and so the interval, as I said, was t2 minus t1, so we denote the interval as bracket t1 comma t2, and the parameter is lambda t. So if t1, t2, and t3, t4 do not overlap, then random variables nt1, t2, and nt3, t4 are independent. And the stochastic process is formed from the points ti, and so we're given the process x of t is equal to n bracket 0 comma t, and it is a discrete state process, which means that it's an increasing staircase, and there's a discontinuity at ti. So there's discontinuity at basically at every step the staircase goes up, and so the mean or expectation is equal to lambda t, and so we can see that's linear, which makes sense if we have a increasing staircase. And the autocorrelation is r1 t2 is equal to lambda t2 plus lambda squared t1 t2 when t1 is greater than t2, and lambda t1 plus lambda squared t1 t2 when t1 is less than t2. And the autocovariance is equal to lambda times the minimum t1 t2, or lambda times t1 times the uniformity of t2 minus t1 plus lambda t2 when it's uniform in t1 minus t2. The next process is the Poisson increment process. So the process, it's also, so I also denoted x of t at the t is greater or equal to 0, and so that's defined by x of t is equal to n t plus epsilon minus n of t over epsilon, where epsilon is always positive and it's a given constant. And n of t is the Poisson process, so it's kind of similar to the previous process, only more expanded. So covariance is stationary, and the mean expectation is just equal to lambda instead of on the other with the Poisson process, the expectation was equal to lambda times t. So the first order probability masses, we have the probability of x of t being equal to n over epsilon is equal to e to the negative lambda epsilon times lambda epsilon to the power of n over n factorial, and the autocorrelation is equal to lambda squared when t1 minus t2 is greater than epsilon, and lambda squared plus open bracket lambda over epsilon minus lambda times t1 minus t2, the absolute value of that over epsilon squared when the absolute value of t1 minus t2 is less than epsilon. The autocovariance is equal to 0 when the absolute value of t1 minus t2 is greater or equal to epsilon, and it's equal to lambda over epsilon minus lambda times the absolute value of t1 minus t2 over e squared when the absolute value of t1 minus t2 is less than epsilon. So from these, we can see that lambda doesn't actually depend on epsilon. The change in epsilon does not affect lambda. And yes, the next process is the Poisson impulses. And so from the textbook, if the input of x of t to a differentiator is a Poisson process, the resulting output, z of t, is a train of impulses, where z of t is equal to the sum of all alpha times t minus ti. This is a stationary process, and the mean is equal to lambda. The autocorrelation is equal to lambda squared plus lambda. So this is z of t is equal to the sum of all the t minus ti differentiated. That's not an alpha. And then the autocorrelation is lambda squared plus lambda times the differentiation of tau, where tau is t1 minus t2. And the autocovariance is lambda times this differentiation of t1 minus t2. So one application of the Poisson impulses is that z of t minus lambda is an example of white noise. So this is something used when we come up with white noise process. So the next process is the semi-random telegraph signal. So this is essentially what it looks like, and the number of sign changes in tau, which is t2 minus t1, is a Poisson process, i.e. the probability of getting k points in 0t is probability of k, which is equal to e to the negative lambda t times lambda t to the power of k over k factorial, and x of 0 is equal to 1, which we can see here in the middle. And so the process is written as x of t is equal to 1 when k is even in 0 to t. And then the probability distribution looks like this. So probability of x of t equals to 1 is equal to e to the negative lambda t times e to the lambda t plus e to the negative lambda t over 2. And then it's equal to negative 1 when k is odd in 0 to t. And the distribution looks like p of x of t is equal to negative 1 is equal to e to the negative lambda t times e to the lambda t plus e to the negative lambda t over 2. So those two are different. With one of them you add the 2, and in the negative you subtract. And then the mean of the semi-random telegraph signal is e to the negative 2 lambda t, and the autocorrelation is e to the negative 2 lambda times the absolute value of t1 minus t2, and the covariance is equal to e to the negative 2 lambda times the absolute value of t1 minus t2 minus e to the negative 2 lambda times t1 plus t2. The random telegraph signal is very similar, except the probability of a being equal to 1 is also equal to the probability of a being equal to negative 1, which is 1/2. Here we set x0 equal to 1, but in a random telegraph signal, you don't set x0 equal to 1. And so the process, you could write it as x of t, but just to make it different from the semi-random telegraph signal, it's y of t is equal to alpha times x of t. And so the mean is equal to the expectation of alpha times x of t, which is the same as writing expectation of alpha times the expectation of x of t. And alpha is just a constant, so you end up with 0 times the expectation of x of t, which is just 0, or another constant. And then the autocorrelation is equal to e to the negative 2 lambda times the absolute value of t1 minus t2, and the autocovariance is equal to e to the negative 2 lambda times the absolute value of t1 minus t2. Okay, the next process is the random walk. So the random walk is a path that consists of a succession of random steps. So we have the probability of x of t is equal to x times n times t. Sorry, x of n of t is n times t is equal to rs, which is equal to the probability of 2k minus n. Probability of 2k minus n equaling r, which is equal to the probability of k being equal to n plus r over 2, which is equal to the series of n. So there's n in the top of n is x1 here, and then x2 is n plus r over 2, and that's multiplied by 1 over 2 to the power of n. The mean is equal to 0, and the autocorrelation is equal to the expectation of xt1 times xt2, and that's equal to the minimum function of nm times s squared, and that's also equal to the autocovariance. So in the random walk, as you increase the number of steps, which is n, to infinity, so basically as n approaches infinity, we approach the normal distribution, or a Gaussian process. In the Wiener process, this is another name for it would be the Brownian motion. This is a limiting process of the random walk process. So that's from the nodes, and so the way we denote it, we go W of t for, it's W just because it's called the Wiener process, is equal to the limit as s approaches 0, t approaches 0, and n approaching infinity of x of t. Where in this case, we would consider x of t as the random walk. So we have the mean being equal to 0 again, and this time the autocorrelation and the autocovariance are similar to those in the random walk, only instead of it being multiplied by s squared and being a function of n and m, it's a function of t1 and t2, and it's multiplied by a constant. The probability density function looks like f of wt being equal to 1 over the square root of 2 pi times alpha t times e to the power of negative 1/2 w squared over 2 alpha times t.